No problem. Okay. So are you ready? Let's start.
As you like.
Yeah. Hello, good morning and good afternoon and good evening. And warmly welcome you to this World River and Delta System, the South to Think webinar series. And today we invite Professor Xixi Lu from National University of Singapore and his PhD student Dongfeng Li come here talk about the global warming impact to the Himalaya mountain area. So the riverine sediment load response to climate change in that high mountain Asia area. So before I introduce Xixi and Dongfeng, I want to mention this coming Friday. We have other talk given by US Dean Nicholson from UK. He will talk about other very interesting river, the Amur River or the Heilongjiang River. This is the river between the China and Russia. As I mentioned last week, this is a relatively unstudied river. We know a very little about this river and the delta system. So please mark your calendar coming here this coming Friday, the same time. And Xixi is, as I mentioned, is a professor in the National University of Singapore, and he got his PhD from University of Durham and Department of Geography. And so he is a co-editor, Singapore Journal of Tropical Geography, associate editor of Hydrological Process, editor board of Earth Surface Process and Landforms. Xixi is a physical geographer with research and teaching experience in fluvial geomorphology, and particularly in the river sediment and carbon flux in large Asia river system. Like he has been studying the Yellow River, the Yangtze River, the Pearl River, Red River, the Mekong, the Salween, and the Irrawaddy. And he co-organized many workshops and also guest editor for the Quaternary International. And Dongfeng, as I mentioned, is last semester of PhD. Will get a PhD very soon. And Dongfeng is also a very active, promising young fellow. He has already published 5 leading author articles in very well known journals like GRL, Water Research, and ESPL, geomorphology, etc. So I think I already talked enough. So now I want to give the floor to Professor Xixi. Xixi, please share your screen and for the presentation mode. Yeah, go ahead.
Okay. Okay, can you see
it's
the
good.
screen now? Yeah,
good.
Although it's not a full screen now, I understand. Yeah, sorry about that. Anyway, thank you, Paul, for your introduction. As Paul mentioned, today's talk will be shared with my PhD student, Dongfeng. Actually, he will talk the most of the slide. I just talk the beginning around the 10 slide. The topic for today's talk is the fluvium sediment responses to climate change in high mountain Asia. This is also a new project I just started this year and funded by the Ministry of Education in Singapore. So where is the higher mountain Asia? I don't know if you have heard of this name or term. Basically, this area refers to Tibet Plateau and it's surrounding mountains like Himalayas and Hindu Kush and the Karakoram. If you move to the further northwest, and that also include the Kherson Mountains. Okay, and as we know, this is a headwater region of many interesting rivers, particularly for our
Wow. Do you think you can cover the whole thing? If you can, let's go ahead do it. And
okay,
if
I will,
he
I will have a try.
yeah, if he log in, then we
goes
give him a chance to talk to answer the question.
really okay. Thank you. I'm really sorry for the technical issue, and I will try to take this slides. So now I will share my screen.
Yeah, go ahead. Okay, go ahead.
Can you see? Yeah.
Yeah.
Okay, thank you. Hello everybody, I'm Dongfeng, and sorry for the technical issue, and thanks Paul for giving me the chance to speak. And I'm still a student, so please feel free to interrupt me if you have questions. Xixi has mentioned that our study area is focused on the high mountain Asia. It is a new term, but it is basically located in the Tibetan Plateau and also the surrounding high mountains, including the Himalaya, Hengduan Mountains, Hindu Kush, Tian Shan. So we know that from this study in the Bible, we know that the Asian rivers are very important in terms of the land-ocean sediment transport. So, and we also know that the mountains are often the most important sediment sources, and therefore we can see that the high mountain Asia, they are globally important in terms of the global land-ocean sediment transport. So that's why we study this, focus on this area. And actually, the high mountain Asia is the climate change here is very fast. For example, the climate warming is warming at a doubling rate of the global average since the 1950s. This is because of the high elevation effect. And the precipitation here is also overall increased, especially after the middle 1990s. So because of the fast climate change, we can see there are many studies, awesome studies that they have looked at the climate change issue, and also the glacier. Glacier is melting, and snow cover is melting, and also the permafrost is thawing and releasing carbon to the atmosphere. And the water cycle is also changing. For example, in this paper, Professor Loss and Imozil, they report that there will be a consistent increase in the high Asia's runoff due to the increase in glacier melt and the precipitation to 2015. So when in 2017, when I started my PhD project, I was thinking how modern climate change can affect the fluvial sediment flux in high mountain Asia. This is the overall fundamental research question for my PhD project. Well, this figure shows the how the climate change they can alter the ELA. ELA is the equilibrium land altitude, and the periglacial processes will occur after glacial retreat, and the sediment flux will increase. And our study area is focused on the headwaters of in the high mountain Asia. Most of the basins are ice-rich permafrost dominated, but they have the very small coverage of glaciers in the upstream. I will go through this because these slides are not my. Okay, so there are three specific research questions. Basically, there are three specific research questions. The first two questions is for the cold, pristine headwater rivers. And we hope to ask what about the sediment source and the seasonal sediment dynamics for the cold pristine river that are underlain by both glacier and also permafrost. And what about the long-term change of the sediment flux? Is there an increase due to climate change? And what about the drivers? And the third question is to try to ask, can we distinguish the impact of climate change from human activities? Because you can see that in high mountains Asia's margin, in the marginal area, there are many dams that have been built, and some of the dams are being constructed or being planned. Let's focus on the first case study area. It is located in the headwater of the Yangtze River. It is the true headwater of the Yangtze and the Tuoduhe headwater basin. It is a high altitude region, elevation range from 4,500 to 6,600 meters above sea level. And it is a monsoon dominated basin and a pristine basin. There's no human activities, no dams, no water transfer projects. So it is a perfect place to look at the climate change effects. The data we use is from this Tuoduhe station, TDH station. It is located in the basin outlet. So to my knowledge, it is the world's highest long-term sediment gauging station for the undisturbed cold environments. And the data here is really awesome. It is it has the daily discharge and sediment concentration data from since 1985. So the data is really awesome. And one point I want to say is that they only measure the data from May to October during the melt season, because in other months the river is largely frozen. The basin, as I has mentioned, that it is a permafrost dominated basin, but in the very upstream there are 2% coverage of glaciers. And here you can see the thermal intrusion features in our warming permafrost landscapes, including the thermokarst lake, the solid fluxion, the active layer detachment, thermal gully, and the source lumps. So here I want to say that the channel connected source lumps are really important sediment sources for this basin based on our field work. And in addition to the glacier snow melt and the bent intrusion are also important sediment source. They can produce both fine-grained sediments and also the coarse-grained sediments. The river pattern here is the braided river systems and with well-developed floodplain. And now let's look at the results. The figure shows the monthly variation of the discharge sediment concentration and also sediment flux. We can see that most of the discharge and sediment flux they occur in the 2 months of summer during July and August, followed by June and September. One point we can see that in September the discharge is still relatively high, but the sediment concentration in September is much lower. And from the rating curve, the discharge sediment relation, we can also see that the discharge sediment concentration relations, they change throughout the season. For example, in September, you can, for the equivalent the level of discharge, the sediment concentration is much lower than other months. And this is related to the permafrost thaw, seasonal thaw processes, and I will explain this later.
Dongfeng,
Hey,
can you use your mouse to point out the data, the curve you are talking about?
Oh, yeah, sorry.
And also speak a little bit slowly. Please go slowly, and because too much information, we cannot catch up. Okay.
Okay, thank you. Yeah. So in this study, we propose a new concept. It is called the active contributing drainage area. It denotes the unfrozen erodible landscape that contribute runoff and sediment processes within a cold environment. So basically, the active drainage area, it is defined the area below the freezing land altitude. So in our basin, during spring, the FLA freezing land altitude is roughly here. So below this area is classified as the active drainage area. And in summer, this land will go upstream. You can see that. So during the summertime, most of the the basin are engaged in producing runoff and sediment. And in autumn, this land will go downstream, so only a small fraction of the basin are the active drainage area. So if you look at the figure, you can see that the red figure, you can see that the relation between the ACDA, the active drainage area, and the discharge, and also sediment flux. You can see there's a very good correlation between the monthly ACDA and the discharge and sediment flux. So we can see that the ACDA is a first order control of the monthly variation of the discharge and the sediment flux for this cold basin. And so what about the specific underlying processes in this basin? In spring, mostly it is dominated by snowmelt processes. For example, here the bottom figure shows the hydrographs of discharge and also sediment concentration. We identified 5 sediment pauses. So the first one, it is caused by in spring, in June. It is caused by the snowmelt intrusion processes. It is clearly seen by the snow cover data. You can see that during this time, the snow cover reduced. It suggests that the melt of the snow pack and associated with the temperature increase, the gray line here. The second sediment pause is in summer is caused by the second sediment pause is caused by the rainstorm events. So you can see that during this time it corresponds well with the rainstorm events. Rainstorm events is defined in our case is defined as the top 1% of all the precipitation data over the past 3 decades. So you can see above the 15 millimeters. So you can see that this corresponds very well. It is driven by the rainstorm events can produce the sediment through both the conventional slope wash and mass wasting. And the third and fourth pause, you can see that during these 2 periods, the precipitation, the green bar here is very low, but the temperature is very high. So they are caused by the thermal-driven geomorphic processes. For example, the glacier melt, permafrost, soil slumps, and thermal gully processes. In this study, we also explained the impact of active layer freeze thaw cycle on the discharge and sediment concentration dynamics. For example, in the bottom right figure, you can see that from May to August, with the increase of the temperature, both the sediment concentration and also discharge, they increased from May to August. And this is associated with the increase of the permafrost active layer. The active layer is the top layer of the permafrost that thaws during the summer and refreezes in the winter time. However, if you see the data, you can see that from August to September, there is a sharp reduction of the sediment concentration. And this is because in September, in the late thaw season, the active layer reaches its maximum. And during this time, the top layer of the active layer becomes dry because there are more infiltration. So during this time, the late thaw season, the runoff regime, it is groundwater dominated regime. So, which means there are less surface flow and less surface erosion. So the sediment concentration is very low. We also explained that the rainstorm events is often determines the peak SSC events. The peak SSC events is also defined as the top 1% of all the sediment concentration data over the past 3 decades. For example, in 2008, we can see that after 5 days rainstorm events, it triggered a historical sediment concentration peak. It is 7.4 kilogram per cubic meter. This number is really large, and it is comparable to many large rivers, I think. And historically, most of the big SSC events are driven by rainstorm events and followed by glacier permafrost melt and snow melt. Okay, now let's move to the next question to look at the long-term change of sediment flux. The data here shows that the long-term change, long-term data over the past 3 decades, from 1985 to 2017, the precipitation, temperature, runoff, and also sediment flux. So we can see if we use a petty test, it is a statistical test, it can give you there's an abrupt change after 1997. So then we have 2 periods to compare, the baseline periods before the 1997 and the change period after 1997. If we compare the 2 periods, we can see that the runoff increased by 80% and the sediment flux increased by more than double, 135%. So this figure is really alarming. It reflects how fast our landscape is changing, and the change of the landscape can be reflected by the fluvial sediment flux data. And this is in response to the warming climate and also the wetting climate. Here in our case, the temperature over the past 3 decades increased by close 1.5 degree, and precipitation increased by 30%. So if we compare our data with the global studies, we can see how unique our data set is. So for example, in this work led by Nathan and also Professor Stuart Lin, they say that we know little about the effect of modern climate change on the landscape at the decadal time scale, because the complex, nonlinear, and pathway-dependent nature of the response of a landscape to climate change, and also because of the difficulty of quantifying spatially distributed impacts at the time scale of decade to centuries. So here, the conclusion, they say that the landscape response to climate change is not necessarily reflected in the valley system processes and the on-sediment deep phase. And another study led by Amy East, they look at the geomorphic and sedimentary effects of modern climate change in the Western US. So here, their conclusion is that they found the evidence of climate change on the slope stability. So there are more slope instability and also the increased aeroline activity. However, they, according to their data set, according to the USGS data set, they don't see the increased sediment flux signal based on their data set. This is likely because most of the basins, even the headwater basins, they are disturbed by human activities. And in the Russia Arctic, we can see that here they have the 6 decades data, and most of the data, they don't show an increased signal. But for this Kolyma River, it shows us increase, but also they attribute to this increase to the good mining activity. So also there are permafrost thawing processes, but the human activities strongly disturb the signal. So we can't 100% sure say this is caused by the climate change. And in the Arctic, for example, in the Greenland and the Antarctic, there are also awesome studies to look at the glacial erosion due to climate change. However, we know that so far there are still no long-term observed sediment flux data in the Greenland and also the Antarctic. So here I want to say, compare with the global studies, our data is really unique, and it reflects how modern climate change can change our landscape so fast. And so how climate change can increase the fluvial sediment flux? On the one hand, temperature increase over the past 3 decades, it can expand the ACDA, the erodible landscape, and to allow more thermal and pluvial driven geomorphic processes within the cold basin. And also in our case, we also found that over the past decades that the rainstorm events are increasing. For example, you can see that most of the more rainstorm events have triggered more fluvial extreme events, including more extreme sediment concentration and also more extreme discharge events. The remote sensing data also show that the source lumps are increasing for our study area, led by Professor Luo in the Lanzhou University. And here I want to say that the source lumps for the permafrost basin, it is really large scale, and most of the time they can, some of the time they can, the spatial scale of the source lumps can be several kilometers or even bigger. So once they are connected with the river channels, they are very important sediment source. And actually here is a video I want. I'm not sure I can. I'm not sure whether you can see how the landscapes are changing. It is in the headwater of the Yangtze River. It's a permafrost basin on a slope. You can see how the landscape are changing due to climate change. And in this event, it is called the earth flow, and it destroyed a car and also a house nearby. Okay, so based on our understanding of the sediment sources within the basin and also the seasonal underlying processes, and also the long-term change of the sediment flux, we propose introduce this conceptual framework to better explain how modern climate change can influence the fluvial sediment flux. So basically, with the temperature increase, it can enhance the glacier melt, thermal-driven geomorphic processes, including glacier collapse, glacier abrasion, and also permafrost soil erosion and stone melt erosion. And with more precipitation, it can enhance the slope wash processes and also mass wasting. And in our basin, with in our warming and wetting climate, the runoff is also increasing, so it can cause more bank erosion. And with all the buffering systems within the basin, we can see that the sediment flux is increasing very fast within this basin. So if we know that temperature and the precipitation are the two fundamental factors that influence the fluvial sediment flux, so if we want to know their quantitative relationship, our data shows that the sediment flux, they increase non-linearly. Specifically, it is an exponential correlation between sediment flux and the temperature. And for the precipitation, it is more likely a linear correlation between the precipitation and the sediment flux. And in this study, we also introduced attribution method to hopefully we hope to quantify the relative impacts of precipitation and temperature. We hope to know that the increased sediment flux is caused by more likely caused by the thermal-driven processes or more likely caused by the pluvial-driven processes. And there are 3 steps to do the attribution. I will not go details. But if you are interested, you can go to the paper, but I will show the result. Shows that here in this figure, all the figures on the loops are the contribution to the sediment flux, and also the contribution to the increased runoff and also increased sediment concentration. So here, our result shows that the temperature increase is the major cause for the increased sediment flux. It contributed to 65% of the increased sediment flux, and the enhanced precipitation, they contributed 35%. Implication for the future. Well, this study led by Professor Wang Tao, published this year in Nature Climate Change. They based on the climate scenario that predict and also the hydrological model, they project that for this in the Upper Yangtze River, that the total runoff they will continue to increase throughout this 2100 throughout this century. So the peak here, the peak runoff is not a peak water. Peak water is the peak glacial water. Here, the peak runoff is the peak annual total runoff. So they will continue to increase, beyond the 2100. Here, our hypothesis that the peak sediment will arrive decades to centuries later than the peak runoff. We explain this by as a periglacial concept, because you know that when the glacier retreats, there are a lot of materials left by the glaciers that are easily to be mobilized by the fluvial processes and also mass wasting processes. So this processes after the deglaciation is called the periglaciation, proposed by Church et al. And this periglacial processes in many study regions they have predicted that these processes can last centuries or even to thousands of years. We think that the peak sediment will arrive much later than the peak total runoff. So here our hypothesis is also supported by the recent modeling study led by Ian Ilani. So he from his modeling studies that you can see that here you can see models or the post runoff and also the sediment flux over the next 100 years. You can see the peak discharge is roughly here in the next 40 years, and within the next 100 years, the sediment flux they continue to increase. So with this hypothesis that the sediment flux will continue to increase throughout this century, throughout the 2100, based on our disk drive model, we predict that the future sediment flux in the Upper Yangtze River at the Shigu station. We choose this station because it is above this station. So far, there are still no dams, but below this station, there are several dams that have been constructed. And we can see from the historical data, the red line is the sediment flux data over the since 1960. It is increasing drastically, and we predict that over the next 80 years, from 2020 to 2100, there would be 5,800 million ton sediment that would be trapped behind the dams downstream of the Shigu station. The hypothesis is that there would be no dams above the Shigu station. Yeah. Now let's move to the next question. Is to try to look at how can we distinguish the impact of climate change from human activities, because you see that there in the marginal area there are a lot of dams have been constructed, and we focus on the Jinsha River. It is the Upper Yangtze River, one part of the Upper Yangtze River. We choose this station because this river, Jinsha River, because historically the Jinsha River is the largest sediment source in the Yangtze River. Historically, it transports roughly from the black dots. You can see that roughly 300 million ton sediment per year. However, after 1999, when the R10 dam began operation, the sediment flux you can see from the Jinsha River, they reduced significantly. And after 2012, when there are more big dams, some Chinese colleagues know that the Baihetan Dam and the Xiangjiaba Dam or Xiluodu Dam, they are very super large dam on the mainstream of the Jinsha River. So after 2012, the sediment flux from the Jinsha River, they reduced almost to zero. Another case is the Jialing River Basin. The Jialing River Basin is historically it is the second largest sediment source for the Yangtze River. it transports roughly 200 million ton sediment flux per year. And also, you can see you can see because of the human activities and also climate change that the sediment flux reduced significantly in recent years, the red line here. And for this basin, the Jialing River Basin is more complex because it has different types of human activities. In addition to dams, there are also reforestation projects. For example, from this paper, we can see that in the last decades, that China's reforestation project has captured the world's attention. And actually, in the Upper Yangtze River in the southwestern China, before the construction of the Three Gorges Dam, the government implemented large-scale reforestation projects after the 1980s and also after the 1990s. So here the question is, can we isolate the relative impact of damming, reforestation, and also climate change? Here we introduce multiple, so-called the multiple double mass curve method. And the assumption is that the dams doesn't affect the mean annual runoff. So with this assumption, we can isolate the impacts of climate and also the impact of reforestation and dams. I will show the result. So our result shows that dams is the major cause for the reduced sediment. It contributed roughly 60 to 70%, and followed by climate change and also reforestation. From the red figure, you can see that it shows the NDVI data. NDVI is the normalized difference of vegetation index. You can see somehow it reflects the vegetation status of the basin. You can see that over the past decades, since 1985, the NDVI increased significantly. This is associated with the reduced sediment flux. And here we can see that the reforestation project in the Upper Yangtze River, they have conserved the soil and reduced the erosion, and the contribution is roughly 10 to 20%. In different basins, they are a little bit different. We also analyzed the impact of the Wenchuan earthquake and on the fluvial sediment flux transport. We know that the Wenchuan earthquake is one of the largest earthquakes in this century, and it has triggered a lot of extensive landslides, debris flows, and this slow processes, the sediment has been transported to the fluvial systems. And we can see from our data after 2008, the sediment flux, there's an uplift. It shows the increased signal, and because the Wenchuan earthquake mainly influenced the left part and the mainstream of the Jialing River Basin, and for this the red part, the Qujiang River, it is still far away from here, so there's no signal in this basin. However, this increase caused by the earthquake is continuous, doesn't continue very long. It also lasts roughly 5 years, because in 2014 there's a Mag Dam, the Tingzikou Dam, that have been operated in the mainstream of the Jialing River. It is the largest dam in this basin. So we can see that after 24, the increased signal, they disappear. So from this analysis, we can also see that historically the increased sediment flux due to earthquakes, due to the mass wasting processes, can be transported to the downstream, the lower part of the Yangtze River. However, with the many dams that have been built directly in the Upper Yangtze River, so all the sediment, even the earthquake, the impact of the earthquake cannot be seen easily. So the implication for the Three Gorges Dam, we know that it is the world's largest hydropower project. And because of there are more dams now in the Upper Jinsha River and the Upper Jialing River Basin, so the sedimentation in the Three Gorges Reservoir, they decreased very sharply. From here, you can see the sediment input to the Three Gorges Reservoir, the red dots here, it reduced, especially after the 2012. And the green dots here, it shows the the reservoir sedimentation based on sediment budget method. You can see that after 2012 and 2013, the sedimentation in the Three Gorges Reservoir is reduced significantly. And in 2018 or 2019, I heard that there's almost no net zero sedimentation in the Three Gorges Reservoir. The world's largest reservoir is really interesting. So it is good for the Three Gorges Reservoir, but it also means that there will be no sediment being transported to the middle lower Yangtze River. And for example, in this Yichang station, we know that it is directly downstream of the Three Gorges Reservoir. So you can see that in recent 5 years after the operation of the Three Gorges Reservoir, the sediment flux reduced almost to zero. The broader implication for the downstream, since historically we know that the upstream basins are the sediment source, and this sediment source will be transported to the delta and estuary and continental shelf. However, in recent years, because of many dams in the upper Yangtze River, and the sediment produced from the upper Yangtze River basin have been directly trapped in the Cascade dams. So it means the clean water released by released from the Three Gorges Reservoir, they will erode the riverbed and cause channel incission, bank erosion, and also the shrinkage of the channel bars. So these two studies are really good work led by Professor Guo Leicheng and also Professor Dai Zhijun. And this is really awesome works that have explained the downstream effects of downstream geomorphic impacts of the Three Gorges Dam. Actually, I also did another study to look at the downstream geomorphic impact of the Three Gorges Reservoir, but focus on the mid-channel bars in the middle Yangtze River. So our data shows that after the operation of the Three Gorges Reservoir, it has caused a lot of issues for the middle lower Yangtze River. For example, the channel incission, bank erosion, and also mid-channel bar shrinkage. This figure shows the area variation of this island. It is an island in the middle of the river. It is just downstream of the Three Gorges Dam. You can see that the island area it decreased by roughly 30% from 2003 to 2015. So you can see how the hungry water can erode the island. And for this cross section, it is also in this bar. You can see that on the left side, the channel incised roughly 10 meters. But this is for this typical cross section. But the overall channel incision for the middle lower Yangtze River is roughly 1 to 2 meters depth. But this process is still continuing. And the bank erosion, for example, for this cross section, you can see that the bank retreated by 150 meters in just several years. This is a really fast change. Finally, broader implication for the sediment source to sink concept. So according to Professor Shu, he is a very well-known fluvial geomorphologist. I believe everybody know. So he classified our river system into 3 zones: the upstream source zone, the middle lower part as the sediment transport zone, and the downstream part as the sediment sink zone. However, for the river system in the Anthropocene, with both climate change and the Cascade dams, the sediment sources in the upstream basins are increasing due to the glacier enhancing glacier melt and also permafrost thaw. And however, this increased sediment source have been directly transported, trapped in the upper Yangtze River due to behind the Cascade dams. And because the clean water, the hungry water, they will erode the riverbed. So the middle lower part of the basin has now become a new sediment source through channel incission, bank erosion, and also the shrinkage of the channel bars. And the sediment sink in the delta, in the continental shelf, has decreased in the Anthropocene. So this is the conclusion here is based on the Yangtze River. I think it also applies for many other big river systems. For example, the Mekong, the Amazon, maybe. Yeah. So my thesis contribution is focused on the source zone, to show the increasing sediment flux signal due to climate change. The final conclusion. So for cold mountainous environment, we think that the erodible landscape, or the ACDA, is not static. It evolves with seasonal variation of temperature. And for the cold pristine basin that are underlain by glacier and permafrost, the temperature regulates the seasonal patterns of sediment dynamics by controlling the ACDA and also the multiple thermal processes. Rainstorm events often determine the extreme events. And over the past decades, runoff and sediment flux have increased substantially. And in a warmer and wetter future, we predict that the sediment flux will continue to increase beyond the 2100. And for the dammed rivers in the marginal area, with future cascade damming, we think that the rising sediments would be trapped behind the cascade reservoirs in HMA's margin, and the relative impacts of damming, reforestation, and also climate change can be disentangled. And also the sediment source to sink processes are completely changed in the Anthropocene. Well, thank you. I will also take this opportunity to thank our collaborators, including Zhiwei, Yinjun, Yuena, and also Albert. They helped us a lot during the field work and the paper discussion and inputs. And also we thank Professor Bob Watson, Professor Tom Dunn, and also Professor Das Walling for providing very constructive comments to our previous papers. Thank you. Thank you for your time. And I'm happy to take your questions.
Okay, thank you, Dongfeng, very much, and particularly thank you for saving the situation. And actually, I called Professor Xixi. I just saw he just relog in, and this is still the winter break for the Chinese Lunar New Year. I guess he's in his office. His building just lost the internet connection, and maybe they upgrade something. And but now I saw him back. So Xixi, do you want to add anything more?
Not really. I guess many apologize for this. I was not aware of this until I finished my talk. I don't know which slide I wanted to. But when
you can still share, Dongfeng go through most of the stuff, but if you want to see a couple of minutes, that would be great. You still can share screen.
I didn't say many of the slides in your part. Yeah, you can.
Yeah, which one? From which one I got lost?
Maybe just the second one, I guess. You just started actually.
Yeah. Oh, really?
So. Yeah.
Oh my God! Then I didn't know you until I asked you and Dongfeng say you can share now. Then I realized that my God, there was no response. Also, I got lost very earlier.
Yeah.
Oh, I don't know.
We worry about you. We are afraid of any heart attack or any health issue, but I'm very glad you're back.
No, I'm still healthy. That will not happen. But I was not aware of until I finished my talk. Then I asked you and Dongfeng, you can share now. Then I realized, wow, my God, no response from you guys.
Okay, please go ahead. If you want to share screen, just go through quickly a couple slides. Because then Dongfeng didn't really talk about much about your slide.
Yes.
Oh, okay. I tried to. Let me find out if.
This is the first time we have this kind of incident, but it's okay. We cover most of stuff.
Yeah, apologize for that.
That's fine.
Let me find out. I guess. Let me find out my.
Just open your PPT and share screen.
Yeah. I run back to my home now.
Are you back to your home?
Yes.
Oh, I'm sorry.
Because the internet is still
Still not available on your campus. I
Can you
know
see
it's
my
winter
screen?
break.
Can you see the screen now?
Not yet.
Oh, really? Oh, okay. My God. Don't know what is going on, Paul.
No, that's fine. Don't worry about it. It's okay. Yeah, it's no.
Share screen, right? Share.
No,
Yeah.
not,
Okay.
not.
Yeah.
Oh, now it's coming.
Now it's
Okay,
coming,
good,
right?
good.
Okay.
Now it's good. Go ahead.
So I don't know which one I
Go
get.
ahead.
This one.
Yeah, you just started this one. You know,
Okay.
we lost you.
I guess since it's almost 1 hour, I guess I don't want to talk too much because there were basic stuff. So what I wanted to mention is this double mass curve or triple double mass curve. It's a straightforward method, and it's very simple, yet it's robust to separate the contributions from some of the control variables. For example, in this a particular studies of 8 large Chinese rivers, we actually separate the contributions from at least from these 3 variables by precipitation and by water reductions and by mechanical retentions of sediment, including reservoir constructions, sand minings, and vegetation recovery as well. And interestingly, you can see for the south, for the rivers in south of China, that is subtropical regions, actually the precipitation has been increasing, and that increased the water discharge and also the sediment load. But overall, the sediment load has been declining. So this kind of information has been buried within that overall declining. You cannot tell, right? But through this work, we can actually find out the precipitation actually could potentially contribute the increase of the sediment, okay? And more interestingly, and we use this simple method, can actually assess the sediment load sensitivities to climate change, water discharge sensitivities, and sediment load sensitivities. And you can see from the empirical regressions, and 1% change in precipitation and can potentially result in 1.15, roughly over 1% of the increase in water discharge. But for sediment, right, it's a double. So 1% change in precipitation can increase or reduce the 2% of the sediment load. So in other words, sediment, it's a much sensitive to climate change. In this case, it's water. Okay, and you can see also water and sediment sensitivities to temperature change. Okay, for sediment, and 1 degree increase in temperature can result in 29 or 30% of sediment decline. Okay, and this result is consistent with Prof. James Sawatsky's work. Basically, Prof. Sawatsky found that for every 2 degrees warming, and that decreased the 18% of sediment in tropical environment. So for large Chinese rivers, it's a majority of the landscape located in the not tropical but the subtropical and temperate environment. Okay, and of course, in the higher latitude and high altitude regions, increase in temperature will increase in the sediment load. Okay, so my point I wanted to what I wanted to make is this simple method seems robust to attribute the contributions of the major controlling variables, because we know there's no better way or method to do this. Okay, so I guess that is what I wanted to talk, and maybe we move to the question and answer
Okay.
lot. Yeah.
Okay. Thank you, Xixi. Once again, I think your team did a wonderful job. Help us understand exactly what caused that water and sediment load change. With complex issues, could be driven by climate, could be driven by the human activity. Even we don't know what's caused by the dam or deforestation or reforestation. All the factors. I think this is a very important work. So anybody, if you have any question, please go ahead, unmute yourself and ask Xixi or Dongfeng. Okay. Okay, Dongfeng, I have a question. On your slide, number 43, you mentioned almost in 2015, because the Three Gorge Dam, there's almost no sediment really released at downstream of the Three Gorge Dam. What's the main reason? I mean, that's a very serious problem. Because in the beginning, starting from 2003, we still receive some of sediment to bypass the Three Gorge Dam to the downstream. So can you share your screen at the 43, your slide?
Yeah. I think it's for, let me see.
43.
This one, yeah. Can see?
Nope.
No.
Now it's moving.
There are some problem. I know your question. Yeah. In the Yichang station, at the Yichang station, there are the sediment flux after in recent years. It's almost to zero, right?
Mm-hmm.
Yeah. I know. Yeah. I think it's not. It's still there are several roughly 10 million ton sediment. It's not zero. Not
Yeah. Can you
zero.
move up a couple slides? This is 49. Can you go up a couple 43?
This is 49. Yeah.
Yeah, use your keyboard, move up.
Let me share my screen.
That's fine. That's okay. Okay, let's move on. Okay, Dave, you have a question? I saw you unmute.
Yeah, very nice talk. Wonderful data set and very interesting and enlightening. My question I have is in their pristine high mountain system where you have the warming occurring, between 1985 and 2017. I'm wondering if the yield, how much sediment is generated per square area, if the yield changes when you have the permafrost move to higher elevation. If you correct for the increased amount of, I know the sediment discharge increases, but I'm wondering if you correct for the increased area that is where the permafrost has melted, is there a change in sediment yield?
Yeah, of course, if you the sediment yield is also changing because the sediment flux are changing. You mean the sediment yield we calculate if we use the active range area to calculate the sediment yield. Yeah. I think it's I didn't do this actually. I didn't do this. Yeah, but if we use the total area, it's definitely increasing. I didn't do this. I can have a try. It's a good question, really good question. Yeah, thank you.
I would think that the yield would increase as the permafrost retreats, because you are in a much steeper part of the water basin, or the drainage basin, so that you would be having the retreating permafrost be in a fairly steep and high sediment generating area. But that is just a guess.
Yeah, I think so. Yeah. Thank you for the question.
So follow this question, Dongfeng. I know many people already published data about the ice coverage change over the Tibetan Plateau, the Himalaya area. So is anybody show the permafrost, the dynamic, the line or the area, the dynamic change because of climate change?
I think there are some studies, but mostly, to my knowledge, they focus on the active layer change. There are also the spatial change of the permafrost. For example, the permafrost change to seasonal frozen ground. Yeah, there are basically the land, the permafrost land is also increasing. I mean, in terms of the altitude, it's increasing from the low altitude to the high altitude region. But most studies, they focus on the active layer because this proxy is seems important in the permafrost community, and the active layer is increasing very fast, and they have the long-term projections in the 2100. Yeah.
Okay.
But overall, the observation for the permafrost in this Tibetan plateau is very rare compared with the glacier monitoring. Yeah.
Okay.
Very often the observations are located along this Qinghai and the Tibet highway. Along this highway, the road.
Oh, I see.
Others are very hard to access. Yeah.
I see.
Yeah.
Okay. Any other question, people? So when we get ready, waiting the questions. So you mentioned you also studied the carbon flux. So do you know anybody done some radioisotope of those carbon from permafrost? The reason I ask is because in US, many studies conduct in Alaska, permafrost, because the preservation of those very fresh carbon, and in the high latitude area, we have a couple talk about food. And so anybody do this from your study area, show the carbon signature change, because that preserved frozen carbon now released to the river.
I guess I have a little bit of experience on the carbon transport and also the carbon emissions from our water bodies. And this was actually one of my proposals. And a few years back, we wanted to quantify the ages of the carbon from in the river systems in the Tibet Plateau and Himalaya mountains. But unfortunately, my proposal was rejected 2 times. And so as far as I know,
that's normal life.
Carbon 14, right? Carbon 14, not many people has done this work on the measurement. Because because many people hypothesis that the carbon actually getting younger. Because of the permafrost degradations. Yeah. Mm-hmm. Yeah, but I haven't seen major papers
on
this.
This could be our future work,
It could
Don't,
be
don't give up. Try the third time. You
Very
will get
good.
it third time.
could be very good research project.
Yeah. Okay. Now it's the 10:20 local time. 10:50, 10:13. Okay. Anybody with any other question? Yeah. Maybe I should, maybe invite you again to talk about more. And so, but today, I think we can stop here. And overall, you have too much information and too much data. And I need to read very slowly because each slide have many interesting figures, curve, and too much. That's very good. Thank you very much, Xixi. And now I know it's 11 p.m. So I'm sorry you run from your office back home. And so I mean,
it's my fault. It's my fault. It's my university's fault.
Well, apparently he didn't inform you. They will have an internet interruption. But anyway, so
this never happened over the past 20 years.
yeah, Okay, I think we can stop here. And